Hi guys, welcome back. In this video, I want to talk about an important concept in real-world systems. And this is the concept of nonlinearities. And we want to see how we can actually model some of these nonlinearities in the systems. Okay, so if you guys remember from chapter 1, we mentioned that a linear system is a system that satisfies two conditions: superposition and scalability. And we mentioned that for a system to be linear, if you're looking at the one input, one output system, okay, when you sketch or draw the output versus the input, it should be a straight line passing through the origin. Okay, we had this behavior in many linear systems that we knew. Okay, for instance, linear springs, if you look at the governing equation as F equals to Kx or delta X, okay, and you plot F versus X, you see that if this is X and this is F, this is going to be a straight line passing through the origin, okay, and the slope of this line is the stiffness of the spring. Similarly, we had the equation for a damper or linear damper that the force was equal to B x dot or delta x dot. Okay, and similarly, if you plot force with respect to the x dot, okay, you see that again it's going to be a straight line passing through the origin, and the slope of that line is basically the constant of your damper B. However, there are times that the system is not linear. For instance, though it's a straight line, but it's not passing through the origin, or it's just showing some oscillations in the system. Okay, so in these cases we're dealing with nonlinearities. Okay, and today in this video I want to talk about an important nonlinearity in the system, okay, which is Coulomb or dry friction. Okay, so dry friction. What is dry friction? Dry friction is basically the friction between the two surfaces when they rub on each other. Okay, so when you have a contact and a relative motion, then you have dry friction. And for instance, if I have a box, okay, with a mass of m, and this box is actually moving, has some motion on a surface, okay, between the surface and the box, let me just redraw the surface here, okay, between the surface and the box, there would be some dry friction that somehow prevents the or resists the motion, okay, or represents the motion of the box. Okay. When you want to model dry friction, there is something that we need to consider. The magnitude of the dry friction is constant, or at least we consider it as a constant. And we show it with F dry. Okay? And the direction of this guy is always opposite direction of motion. Okay? So for instance, if you assume your box is going to the right, okay, then if you want to show the free body diagram for this box, okay, and I'm neglecting all the other forces, okay, and I'm assuming that the box is going to the right. If the box goes to the right, the friction force will go to the left. Okay, and similarly, if the box is actually going to the left, so this is your x naught dot, okay, and this is the direction of x naught dot, okay, and if your box goes to the left, similarly, your friction force would be the same magnitude, opposite direction. Okay? The same magnitude, opposite direction. Now, you might ask yourself why this is nonlinear. Okay? Let's compare this model with F equals to B x dot, which was the viscose model, yes? And in the equation for viscose damper, you notice that you have a very valuable component, which is the velocity. The velocity is directly incorporated in this equation. It's very valuable. Whereas in the F dry, the velocity is not incorporated. If I have a linear damper with a viscose, basically a viscose damper, and I show the friction on my body with the viscose damper, anytime my velocity is flipped like this, that you have here, because I am incorporating the velocity in the model, that velocity will flip the direction of my friction force. Whereas in F dry, I do not have velocity incorporated in the system, okay, and in the model, and I need to somehow manually flip the direction of this force when the direction of motion is flipped. This is one thing. The other thing is, look at the equation for a viscose damper. Since the velocity is directly incorporated in this equation, whenever your velocity is zero, the friction force would be automatically zero. Since you just substitute velocity in this guy, okay, and it's going to give you the friction force zero. Whereas F dry also does not show me zero friction whenever the velocity is zero. Okay, so for F dry, I need two things. I need something that flips the direction of the force whenever the direction of motion is flipped. Okay. Also, I need something that can handle zero velocity. Good. So I need something that can handle zero velocity. Whenever the velocity is zero, it's going to make the friction force zero. Okay. So here's the question. How can I get such a valuable representation or model? Okay. The idea that is, we borrow something from mathematics. We call it as sine function, okay? So sine is SIGN, okay? And but in mathematics, we do not show it as SIGN, we just show it as SGN. Okay, this is a sine function. Let me plot sine function for you guys to see. Imagine that the argument of this sine function is x dot, which is your velocity. This argument can be anything. Okay, so I'm gonna plot sine function here, x dot, and this is the output, or let's say SGN of x dot. Okay. Sine function is an important function. It says that whenever the velocity is positive, it means that you're on this side of the velocity. Okay. Whenever the velocity is positive, the value of the sine function is number 1. Yes. Whenever you're on the right side of your SGN axis or the vertical axis, the velocity is positive, x dot is positive. The value of SGN is always 1. Whenever the velocity is negative, the value of SGN is negative 1. Yeah? And whenever the velocity is 0, which means that you are here, the value of SGN is always 0. Yeah, good. Okay, now look at this. It's very important, yeah? It's a very important function. What we do to model f try is we simply multiply the magnitude of f try, which is a constant number, by the sign of the velocity. If you have relative velocity, if you have just one velocity, that velocity. So let's see how this simple model will handle the dynamics of the system. For instance, imagine that I have a box. This box has a velocity going to the right, okay? And I show the f dry as f dry SGN of x dot. Whenever the velocity is positive, and this is my positive x direction, yes? Whenever the velocity is positive, sine of x dot is number 1 here, okay? So the direction and magnitude of your f dry would be opposing the direction of motion. Whenever the velocity becomes 0, sine of x dot will become 0. Look at this. Sine of x dot will become 0, and basically your friction force disappears. And whenever the x dot would be negative, which means that your box goes to the left instead of going to the right, SGN would become -1, okay? And if you multiply -1 by this vector, you automatically gonna flip this vector, okay, and pointing to the right, okay? So very simply, we handle this model. Now, you might ask yourself why this system is nonlinear, why this model is nonlinear. Okay. The answer is very easy. Look at the output SGN or sine of x dot versus the input. For this output versus the input to be linear, you should have a straight line passing through the origin, something like this. I show it with the green line, something like this. However, you see that though you have basically segments of straight lines, but none of those segments, besides the one that's actually dealing with the zero velocity, none of those is actually passing through the origin. Okay, so this one does not pass through the origin. This one does not pass through the origin. That's why this model is nonlinear. Okay, good. Now, you know how you can handle f dry as a nonlinear function. Let's go to solve an example and see how this is actually going to work out. Let's go back to our solenoid valve. If you guys remember, when we wanted to model the solenoid valve, we mentioned that, okay, we are going to assume that the only friction that we have is a viscose model. This was our example 1, yes? That was a viscose damper. Now, what I want to do is I'm going to assume that I have a little bit of f dry between the spool and the plunger and the wall. Okay, and I'm going to show that f dry with this symbol or notation. Yes? Okay. So let's go and see how we can actually incorporate this nonlinearity in the model. So what I'm going to do is I'm going to first list the elements in the system. Yes? So let's go ahead and list the elements in the system. Okay. Inertia, stiffness, friction, my sources, and the number of ODs. Good. Okay. If you look at the schematics of the system here on the right side, you see that I have only one mass element. Since it's a mechanical translation, I'm going to include that mass as my inertia element. Also, my stiffness element is basically the return spring, which I'm going to show it with K. My friction elements are first the viscose friction, which I'm showing it with a viscose damper, and also a dry friction here. So I have two friction elements, yes? So this is going to be F dry and viscose damper. The source in this system is, again, electromagnetic force, okay? And I'm going to show it with F electromagnetic. And at the end, you guys will know that the number of ODs is basically the number of inertia elements in the system, naively speaking, okay, which is not 100% accurate, okay? And we said that we are going to fix this at the end of this chapter. Yes, so I have one inertia element, I would end up with one OD. Okay. This is the preliminary. I know what's going on in this system right now, okay? Then I can jump to my first step. Step one is selecting our coordinate system. For this problem, again, my assumption is that the gap here between the wall and the spool is the same amount of the free length of the spring, okay? So I would consider seated position or the free length of the spring as the origin for my coordinate system. And I'm gonna consider going to the right as the positive direction, okay? So going to the right and measured from the seated position or the free length of the spring, okay? So this is X, and I know the origin, I know the positive direction for this guy. Step two is basically isolating my inertia element. In this problem, I have only one inertia element. I'm going to isolate this. It means that I'm going to grab it, I'm going to disconnect it from the system, and I'm going to throw it on a piece of paper. Yes? And I'm just going to show the coordinate system on top of this guy as well. Now, let's go to a step three, which is my free body diagram. And the free body diagram, I would go after view, CSR. Again, friction, external weight, contact, spring rope. Okay, good. Now, let's go after the friction ones. I have two friction forces. One of them is the viscose friction. The other one is the dry friction. Note that we have done viscose friction for this model before, for this problem before. It's very simple. Since one end of that damper is actually connected to the wall, the other end is connected to the mass, the magnitude of that friction force would be x dot. The direction would be always opposing the direction of motion. If the box goes to the right, we assume that we know that the friction force would be going to the left. For the F dry, we have it between the surface of the wall and the surface of the spool and the plunger and the mat, basically. Okay, so I would consider F dry SGN of x dot. And for showing it in the free body diagram, I would look at the direction of motion or assume direction of motion. Yes, if I assume that the box goes to the right, this is going to go to the left. Good. The next one, so I'm done with this guy, yes? The next one is the external force. I know that I have only one external force, and that is F electromagnetic. The direction on magnitude of that guy is given to me. It's pointing to the right. So I'm done with this one as well. The next one is the weight. Should I consider the weight in my free body diagram? Well, I do not have any motion on the vertical direction, so I'm going to neglect the weight. Similarly, for the contact, the only contact that I would consider is the contact normal reaction from the surface, which is pointing upward. I do not have any motion on the vertical direction. I'm going to neglect that one as well. The last one is the spring. Since I do not have any rope in the problem, the spring is the last one. And we have done the spring before for this problem. You guys know that when the box goes to the right, the spring is in compression. It's going to push back against the direction of motion. So it's going to be Kx. Okay. So I'm done with these with forces. Now I can safely navigate to step 4, which is my equations of motion. Okay. In the equations of motion, I would write down the Newton's second law along the x-axis. Okay. Let's go back to our free body diagram. How many forces do you see here? 1, 2, 3, and 4. Among these 4 forces, you notice that only F electromagnetic is in the positive x direction. The rest of them are pointing to the left, which is the negative x direction. Okay, so I bring FEM with positive sign and the rest of them with the negative sign. Okay. Now, let's do a little bit of cleaning. Okay. So I'm going to keep the input, which is the F electromagnetic. On one side, bring all the dynamic terms to the other side. Okay. So F electromagnetic equals to mx double dot plus bx dot plus kx plus F dry SGN x dot. Okay, and you can safely box this equation. This is your final answer. Okay, note that for this problem, because you have the SGN function, okay, and SGN function is a nonlinear function, your system is nonlinear. It's not a linear system anymore. Okay, so it doesn't matter if these terms are all linear. If you have only one nonlinear term and a million of linear terms, okay, only one nonlinear term and a million of linear terms, that one nonlinear term is going to ruin your whole system. It's going to make your whole system nonlinear. Okay. So if you found this video helpful, please subscribe to the channel and follow for more videos. Thank you.